it is.
2 wires are done. And you feel
Wire?
could have been. He said he was farming. Healing.
Green one?
He's not that old. 1950.
World War II? Keep going back.
Yeah.
Maybe short.
He's in the back.
Well, we're gonna take off here. So you remember from day one, I took you outside here and why don't y'all just come back down real quick?
Okay.
Remember on day one, I showed you basically how it works. You get a better idea. But I want you to look at this. This is a compression here and here. But we have a splitting, this is 2 parts of the compression. So this one, each one will turn independently from one another. So this section here is a high pressure compressor. You see, also known as E2. This one here, low pressure compressor. So we have turbines back here. So you're saying really good. Which thing really good? Slip around the side of it so they can see around it. So that's the high pressure turbine. And you can see it's attached to this compressor here. And then the next 2 stages here. Are attached to the pressure compressor. That's M2 or the M1 turbine back there, or the low pressure turbine. So low pressure and high pressure tied together. So high pressure turbine and high pressure compressor are tied together. And that's the low pressure compressor, low pressure turbine. This is what we call a split spool motor. Because from here to here, the pressure ratio change across these stages. So rather than every time you speed up and when it slows down, these two will tend to run together about the same speed. But every time it slows up or speeds down, or slows down, we're going to have this difference of here across these two stages. So what we do is we split these two separate sets of motors. That allows a little bit of flow between the compressors. These compressors are not going to turn at the same speed sometimes. That allows for a little bit more efficiency here, here, and here. These two are running at the same speed, everybody's running at the same speed. And it works perfectly. So aircraft engines are at the same speed all the time. I'm going to throttle up, throttle down. Pitch is over there, throttle back. Now you're forcing it. But this doesn't do this. Started it. We're going to start turning this here. This one, E2. I'm going to start right through the and one will follow one. So this will start going here slowly. The reason we use starting is we want 2 systems. This is really the gas producer process. What we usually do this is also attached to so it's all driven off of two here. And two is IPA set stages of compression here. It's also part of basic part of the engine is called the gas producer. So here, here, and there's turbine. That little compact thing is what drives the rest of the engine. When you start that, you start running this over here, you start turning this motor, raise the pressure, and then here starts moving into the front, starts turning this front here. Now, it's going to start moving so very much air, you're going to see it again. You could put your hand under your hold this way. Start moving, start moving. This part here relies on the air because we drive this one across the next turbine. And that air, that is going across the other two stages of the back. So what we have is we have a fluid coupling between the turbines. We have a fluid coupling between here and here. We have a fluid coupling between one and stage two turbine and back. So two fluid coupling together. Fluid coupling, air coupling.
This is,
Okay, so first slide, you have to look at that. There's nothing in the right down.
not the electric,
Well, it's like turbine flat.
So that is a split spool engine right there. And it's kind of like two engines, essentially in the same engine housing. Now, the earliest engines only had single spools, and they weren't as, because they didn't have as many stages, they worked okay, they worked pretty good. But once you start adding more stages and getting more compression, then you had to go to a split spool design. So the spool shafts, as you could see outside there, are tubular shafts, and you've got one riding inside of another one. So some terms that we've used, and if you haven't written them down by now, do it now. It's a good time. So there's an HPC, HPT. And we're going to start throwing these things around like they were manhole covers. So you're going to be thinking, oh crap, I wish I would. This is okay, so each one of these things are known by different names as well. And so this is going to be known as the N1. Now, if you talk to the N1 compressor, that's what you're talking about right there, N1. Okay. N1 is a engineering designation. Now, a lot of times people just see N1 because it's just as easy to say instead of HPC. HPT is a high pressure turbine. And the high pressure turbine is going to be the N2. Wait, no, that's not right. This is N2. Could be known as N2 or the N2 turbine. Sorry, I scratch that out of the paper.
both ends.
That's the gas producer, right?
Sometimes not. We'll get to that. Yeah, sometimes yes, sometimes no. Depends on the construction of the engine.
They're both N2.
Both of those are known as N2?
Yes, both of these could be known as N2, right? They're part of the N2 system.
What's N-
So if you say N2 turbine, you know exactly you're talking about the height.
What's the N?
N is a engineering designation, just means that N stands for the number, the rotation of the turbine. That's all it means.
That's rotating.
Yeah, I try to track that down from an engineer, and the engineer says, because it's an N, it means number. So number means, I said, so how does that relate? He said,
Two is numbered.
there's no doubt, this is gonna get confusing. Give me something to do it. So put these in your acronyms. So when I give you a test, I'm just gonna put LPC, or I might put N1 or something like that. It could be called the N1 turbine, could be called the N2 turbine, depending on where it's located in the engine. So it's not only what it is, but also where it is located in the engine. We use these terms kind of loosely sometimes. If you haven't written those down, please get those written down right now. So in this engine out here, the gas producer is the N2. Everything in the N2 system is a gas producer in this engine. But that doesn't always hold when you start talking about turboshaft engines and turboprops. Some of that can start switching around on you because the construction of the engine is a little bit different. You're gonna find something else out there. NG and NP, just to confuse you more. So NG is a gas producer. NP is the power turbine. So the ends follow kind of along this line here, except in some engines.
So the gas producer is the from the second.
Could be. How's that narrow it down for you? It could be. And this one out here is the high pressure system in the engine. Yep.
So what's the power turbine in the back end?
Could be way in the back, yeah. Depends on the construction. So when you go out and look at your engines tonight, so you're gonna have your combustion sections off, you're gonna be looking at the turbine. You'll be looking at some stages of the turbine there. So I want you to figure out, in this case, in your engine, which one is the power turbine. You have two stages of power turbine and you have two stages of gas production. So I want you to look at those and see which one is the gas producing turbines and which one are the power turbines. If you reach down through the exhaust pipe, you can feel the other turbine. So you start taking a second call. So you reach down and you feel the turbine, but also if you have the combustion can off, you can look at the other turbines. So there's 4 stages of turbine that you're looking at moving forward in the gas flow or the gas path. So that's a little confusing. Don't worry, I got more. Okay, on a split spool engine, like what we have outside here, the inner spool, if you think about it, you've got two spools there. The inner spool has to run through the outer spool. And the inner spool has to be the one that goes the longest distance. This has to be, that's the way it is. Can't have the outer spool running the low pressure system. So it's the inner spool runs the low pressure system. And then the outer spool, if you need to jump up, go out and take a look. That's what you need to do, is just go take a look. You're welcome to do that. The outer spool is going to run the rear compressor or the N2 compressor. And it's going to run the front turbine. Come on, come on, come on. I know you're all thinking, what the hell's he talking about? Come on out here, take a look. Come on.
C, T, G, L, M, N, O, Apparently.
Almost was that close.
Carriers. C.
Jammed my hand a few times. About the LP shaft going through the LP, basically.
How you have the shaft within the shaft?
Yeah.
You can't run, since your gas producer is the thing that's starting your engine. That shaft can't be on the inside shaft, so there's no way to connect that shaft to the gearbox coming out. So it always has to be that outer shaft, so you can run attached to the gearbox.
Another day entangled. Another day entangled.
Okie doke. So the outer spool or the outer shaft is going to have the rear compressor, HPC, and the HPT, and the inner spool or the inner shaft is going to have the LPC and the LPT in one. Okay? So you'll understand the difference between N1 and N2 now. Okay. And that's pretty typical. Not always, but it's pretty typical. Okay, if you had a turbojet engine, now this is one that just burns fuel, makes a lot of noise, screeches, and puts out a lot of thrust. It's meant for high altitude, excuse me, it's meant for high altitude use. It really just uses split spool because you have so many different stages that you have to have. Excuse me, a little bit of float between the two rotors. Now, turbofan, I'm not going to stop with that. It's going to use an N1 NN spool and N2 spool. Okay. Power producer. And the N2 is going to be the power producer, the gas producer, right? The part in the middle is going to be the gas producer, and the part on either end is going to be the power producer in this case. So on a turbofan, you're running a giant fan, a multi-bladed propeller is what you're running essentially. And that is going to be the power producing shaft. What do you need?
Taking all the fire extinguishers.
Oh, go on in. It's okay. I'm dawdling along here today.
Four, so far, 6 missing.
That's
Reassuring.
We haven't had fire, it's no big deal.
Good. Did we ever put one back outside?
Nope, those are 2 missing.
Oh, nice. They come through here, the facilities people come through here like locusts, you know, they just pick everything up in a big pile, they don't mark where everything goes. And so they take 40 fire extinguishers out of here and they put 30 back. Still a mountain of fire extinguishers, but I guess they figure they get out ahead that way. All right. Now, a turboprop or a turbo shaft is going to turn that around a little bit. It's going to use the N1 for shaft power. And the N2 for the gas producer. Now you may have in a reverse flow design, remember your engines are reverse flow. I want you to look at yours carefully when you go out there again this evening. It may reverse that to where you have N1 and N2 are now going to be used for gas production in a reverse design. So you might have N1, you look at it, the low pressure side is going to be N1. You look at the low pressure side, that may end up being your gas producer. And the N2 might end up being your power producer. So look at your customer training books tonight and see which turbines turn the gearbox on your engines. Which pair of turbines turn the gearbox. And that's going to tell the tale. Now they do that because of the way the engines are built. So in this case, the second or the third and fourth stages of the turbines are very close to the gearbox, and they run a gear that turns the gearbox, and that gear runs the power shaft off of the gearbox, which is going to go to a gearbox, to a rotor head, and then up to the rotors. So things do change around a little bit on reverse flow design. Part of that is helping to keep the thing more compact. So in a turbo shaft, turboprop design, you're going to end up with the gas producer, who's going to drive the compressor. The power producing turbine is going to drive a geared shaft output. There's probably not going to be a compressor attached to the power shaft turbine. So you're going to have a gas producer who'll have, let's say your engine, for instance. Then you've got 6 stages of axial, you've got 1 stage of centrifugal, and that pushes the gas back to the combustor. The combustor gas goes through the combustor, a couple stages of turbine, and that turbine drives the compressor. But that gas, the leftover gas now goes across 2 more stages of turbine, and those 2 turbine wheels are going to be the ones, the power turbines are going to be the ones that turn this geared shaft, and that's going to turn the rotor blades or propeller. It's a little bit backwards. Okay, so then you have a 3-spool rotor. Now Rolls-Royce is famous for this. So, you got a shaft within a shaft within a shaft. Only they're not shafts; they're drums. Is what they are. So they have to start getting bigger and bigger and bigger as they run inside of each other. And so what you've got is you've got the fan up here, which is driven. Follow this line back, which is driven off of these 3 stages of the turbine, the last 3 stages of the turbine. Everybody got that? You all see that? So that's gonna be the low pressure rotor, just called LP. LP, so you got a low pressure turbine, you got a low pressure compressor. Okay. And in this case, you don't have a low or high, well, you do have a low and high, but you have one in between, it's called an intermediate pressure. So this is the intermediate compressor here. 7 stages there. Follow that dark line this way. And there's one intermediate pressure turbine that drives that compressor. And then you're going to have the HP compressor, 5 stages. Follow that slash line, hash mark line back to this turbine here, and that's going to be the HP turbine. So the HP section of the engine is this big. The IP is this big, and the LP goes from here all the way back to here. But do you see how you still have one shaft inside of another shaft to make that work? And it all has to be supported with bearings. So each one of these things supported with bearings, because what happens, you start getting these rotor speeds so high and the masses are so heavy. These engines weigh almost 10,000 pounds apiece. Okay, almost 10,000 pounds apiece. And so you end up with a case of so much mass inside here that these things want to start bending and whipping inside. You don't want that to happen, because everything back here starts going like this when the shaft starts bending, and then you start breaking the shafts and so forth. Okay. So that's a Rolls-Royce engine. Thousands of them out there. They're on everything. That's a popular engine. They're beautiful engines. Freaking beautiful engines. Like machinery. Pratt Whitney, General Electric, IAE, BMW, all of those companies build nice looking engines, but these are gorgeous. These are freaking gorgeous. Look like something an Englishman would build. Okay. They're really good. So this is a 3-split spool RB 211. There's some bigger ones than this, but they all use a 3-spool rotor. So you don't have to worry about that too much. I'm not going to ask you about that so much, but I want you to know that 3 spools exist. In that case, you have an HP, you have an IP, and you have an LP system on those.
And the gearbox is driven off of the HP.
Yes.
The IP, would that be N, like an N3 or something along those
Yeah,
lines?
it'd be N3. Well, it'd be 1, 2, 3. It would be N2 in that case. Yeah, it'd be N2, and then N3 would be the HP system. All right, so we're gonna keep banging ahead here. 6 o'clock. Don't write any of this down, because I'm gonna go over each one of these in order. So we're gonna talk about the inlets today. We've got compressor section, we got the burner section. We're gonna march right from the inlet of the engine all the way out the back tailpipe of the engine, and each one is sectioned in a week. And so you're gonna see all of these things. We're gonna talk about thrust reversers and exhaust sections, augmentation, injection, augmentation. Way over here, injecting water into an engine, turbine engines. Yeah,
Not turbines.
yeah. Well, they do it. They inject it into turbine engines too. There's seal shafts, gearboxes, starters, different kind of starters, fuel control systems, lubrication. We've got a little ways to go here yet. Okay. So we're just going to start with the inlets tonight. So the inlets, and I'll show you some pictures here so you don't go on too. We'll take a break in about 20 minutes, 30 minutes. So the inlets are all kind of designed for different aircraft profiles. So I was doing a job for Pratt Whitney one time up at Long Beach, at Donald Douglas, which is Boeing now, on an MD-11, and they were changing the inlet design, because they wanted to get more fuel economy out of the engines. And so they were testing these engines, and what they found was that when they pitched the airplane up to too high altitude, because there was nobody on this airplane, they pitched the airplane up, and this thing started stalling. We'll talk about stalls a little bit to get the compression. But what that was caused by was the air burbling over the lip. of the inlet. So we've got this big inlet, looks like a tube sticking off the end of the engine. And it's going straight through the air, it's no problem. As soon as you tip it up, the airplane doesn't follow a straight path. It kind of slides sideways as it flies. And so the air was burbling across the lip. So these things have to be built according to the flight profile that the airplane is able to fly. So we're going to be talking about that in just a second. Now, what we want to do is we want to allow a good flow of air into the engine. We want to have maximum inlet pressure. And we're going to be utilizing the inlet airstream to help build that pressure in front of the engine. This helps us, helps the compressor. So the compressor doesn't have to work as hard to compress the air into the engine. So we're going to use that ram air effect being pushed into the engine to raise that pressure. So the duct, the inlet duct, and every engine has one. Their shape and size may differ, but every engine has one. And it's the best, allow the best air inlet under all flight conditions with as little turbulence as possible. This engine has to be able to breathe. Now, there's some factors that be taken into account on this. One is the airspeed and the aircraft attitude. There's friction on the walls of the ducting. There's meteorological conditions, ice and rain, humidity, temperature, the maneuverability of the aircraft. What kind of attitude is this aircraft capable of? And also location of the engine on the aircraft. Is it a mid-mounted engine? Is it hanging off a wing? Is it tail-mounted? Is it a front-mounted engine? All of those kind of things all enter into the design of the inlets. So the inlet surface. The inlet surface, do you remember me telling you that high velocity air is also equated with noise? Remember me saying that? Yeah. So some of the surface conditions on the insides of the inlets are made so that they help cut down noise. There's a couple of different ways to do this. As the air shears across that surface, because that air is moving across that surface at a very high rate of speed. And what it does, it creates a shrieking sound. Well, one of the things that they do with those surfaces is that they impregnate a material. To a company around here called Rohr Industries. Any of you know Rohr Industries? You ever hear of them? Anybody? Okay, it's called VF Goodrich now. But it's a patented material. It looks like screen door. And they impregnated it in an epoxy onto the surface of the inlets. But what that does is that breaks up the airflow across the surface. So the surface doesn't shear now. It's called Dynabrode. Stuff doesn't shear. What it does, it creates a little bit of a turbulence zone between the surface, the skin of the inlet, and the air flowing over it. So it acts like a little cushion between the two. It's just a real thin little surface. It is a little bit of a aerodynamic bubble across the surface, but it acts kind of like a film of bubbles. That's what it does. It acts like a film of bubbles. It just keeps that air from shearing across the surface of the metal. So it cuts the noise down on the inlet significantly. Now, there's a convention, the ICAO, It's an international convention of aviation airlines and airline authorities. And they specify certain noise limits in certain areas, decibel limits. And right now, the most stringent limits are set at Frankfurt Airport in Germany. So and the reason for this is because the houses are building up next to the airport, and the Germans don't like all that noise in the backyards. And so they use these limits that they've set. And so the ICAO comes along and says, okay, well, this is the lowest limit that is possible for a modern aircraft to be built to. So they're not the FAA, but they set a convention of limits and the FAA buys into it. So what happens is they go out and they fly a profile. And the profile could be out in the desert, it could be up in the mountains, could be any place where they can set the noise meters out, and it's in the same shape as Frankfurt, Germany, has the same limits, and so they listen to every aircraft fly over this. Now these aircraft fly over it only a couple hundred feet over the ground. But what they're doing is they're looking for the noise that's being created. They can separate that noise out. They can separate the exhaust noise, the engine noise, and the inlet noise. Separate the three right apart from each other, and they can tell how much noise they're making. Noise is a huge issue with turbine engines, as you might suspect. And getting an aircraft certified, when you have too much noise, well, it just ain't going to happen anymore. So the manufacturers take it on themselves to make sure that the noise is way down. Slight imperfections in workmanship can have major results. This is not only the factory workmanship, but any repairs that you might do. So you're up there working in your Vibram boots, and maybe you got a stone or another or bolt in your boots. Walking around the inlet. First of all, what you say when you walk around in the inlet, you will, some of you will, probably a lot of you will. You walk around, lay down a rubber mat, a piece of cardboard or something, a piece of carpet when you walk around the inlets. You guys do it. Yeah. Because that stuff's soft. So that liner is incredibly soft on the inlets. And if you punch a hole in it, then it has to be repaired. Well, if it's a bad repair, what you're going to have to do is it's going to cost you, because anything costs you whatever 1% loss of air efficiency in the front of this engine, you're going to lose about 1.5% coming out the back of the engine, and all this stuff starts adding up after a point. So you want to make sure that any repairs you do are done according to the component maintenance manual. Give you another one. CMM. CMM, component maintenance manual. CMM, component maintenance manual. So you'll find in the maintenance manual, or the aircraft maintenance manual, you'll find all kind of repair schemes, but when it gets down into fixing some specific little thing, you're going to have to go to the component maintenance manual. Something like an inlet is in the component maintenance manual, it won't be in the aircraft maintenance manual. And while we're on the topic here, IPC. In the civilian world, it's called the IPC, the Illustrated Parts Catalog. Okay. Illustrated Parts Catalog. Now there's some repairs you're going to find someplace else, and that's in a book called Standard Practices. Or the SPM, Standard Practices. While you're writing it, let me go get one. I'll get one and show you. So you're gonna find these guys here, standard practice manuals. You start getting to be kind of big after a while, I'll leave them here, you can look at them. But they cover a lot of things like basic inspection techniques, nothing specific, but basic inspection. Shows you how to bend a cotter pin in there, for God's sakes. It's sort of like the 4313. Anything that's kind of unusual to a turbine engine, there it is. Now, in this case, it's Pratt Whitney. What they do is there's always things that you should know how to do, but they don't specifically outline them in their maintenance manual or in the component maintenance manual, or it may reference you to this manual here. Okay? This is what they call standard practice. It just tells you how to scrub with a Scotch-Brite pad, tells you which way to scrub, tells you what to scrub it with, what chemicals to use with certain materials. If you're going to weld something, what kind of welding rod do you use? It's all kind of little stuff. And it's like the how-to book. It's all kind of little stuff. You're welcome to look at it. So that's the standard practices manual. Now, every engine manufacturer is going to have one. They might call it something a little bit different, but it's going to be a standard practices manual. Okay, so the greatest loss through the inlet is going to be surface friction and turbulence. We talked about this next one here, long ducts, sharp turns, poor repairs. All of that's going to lead to poor performance or degraded performance. Anything that prevents the air from moving in a straight line, deviates from it moving in a straight line, is going to result in loss of performance. So if an engine has those features that causes air to move around a corner, a 90-degree bend, or through a tube some distance, you have to know that the engine is built with enough margin to compensate for those things and still produce adequate power. Okay, so you have stuff that the engine ingests, so it has to be resistant to those things. If it comes in the inlet, you don't want to blow in a hole through the inlet. So it has to be resistant to debris, airborne solids, birds, ice, hail, any of that stuff.
People.
Has to be built to keep the noise down. And also they use them to keep the engine case round. So this not only allows the air to flow through it, but it also keeps the case round. Okay, so I'm going to roll the screen up here real quick because I want to show you this. So when you have a round engine case and you have a heavy rotor in here that maybe weighs 4,000 or 5,000 pounds, and you hit a G load, maybe turbulence, something shocks or a hard landing, and this is supported off of the outside of the case with struts. I'm just going to put 4 on here. In reality, there's a lot more than 4 of them. So this is supporting about 4,000 pounds here, but this is slung to the wing off of this point up here on top of the engine. If you have a hard landing, or if you go through turbulence where the airplane's going down and then up, where there's G loads and then negative G loads, what is the shape of this engine going to take what's that gonna do as soon as those forces are encountered?
I'm trying to make it oblong.
It's gonna try to make it oblong, right? So, and of course that won't do because the rotor's still turning inside there. And that rotor, if it starts digging in, so if this thing starts going this way, the sides get closer, right? It's gonna start digging in on the sides. And so what they do is the inlets have a frame on them, and that frame helps keep the case round. As soon as you bolt it onto this thing, that is another structure that helps keep the engine case round. So it is not only a duct for allowing air to go through into the engine, but it's also a structural component of the engine itself. Good. So the most common design is just a single entrance inlet. It's just a short duct that's used on most multi-engine subsonic aircraft. We're talking subsonic here, we'll talk sonic in a minute, but I'm not going to get into sonic too much. Single entrance, short duct. This is going to be an engine that just hangs out in the breeze, typically. Good. So you've all seen these kind of inlets here, right? You've all seen those pretty much? Okay. So what you have here is, if you look at the design here, and once it gets blown up, it starts to fall apart a little bit. But if you notice, this is known as the lip here, and this is the part they're going to fill with some compressor bleed air. Compressor bleed air is hot, right? And it will have a valve on it or not. The valve will go on or off, depending on how much warm air you want to have in that lip. Because this is going to be a point here where the pressure is going to fall across this lip. And when the pressure falls, what happens to the temperature? Temperature takes a dive. So you could be flying in rain that's 35 degrees, but it could present a problem here because at 35 degrees in rain, it could begin to make ice on this lip. What we do is we heat this whole lip to keep that from occurring. The next thing you'll see that happens here, if you look over on this side here, it's easier to see, is that this is probably the tightest part of the inlet, right through this section here, all the way around. And then it opens back up again. Do you see that? See how it kind of falls away and it creates a diverging duct inside the inlet there? Okay, so that little bit of a diverging duct is going to occur from here back to about here. What that's going to do, that's going to start to raise the pressure in the duct or in the inlet. So we're going to knock the velocity down a little bit. We're raising the pressure in front of the inlet, we're knocking the velocity down. Because we really don't want a lot of velocity up here. But we also need to give the air some direction. So this is just a big blob of air hitting this. So we have what we call a spike or a spinner up here. The spinner is an aerodynamic device. It does a couple things. One, it covers the bearing that supports this whole wheel up here. And all those blades are attached to a wheel and a hub. So it's an aerodynamic device that causes the air to flow over that nice and smooth. But the other thing that it does, it gives the air, as it goes into the engine, it gives it some direction. Right? So it's actually another little converging duct inside of a diverging duct that's going to allow that air to move in a direction that we want it to go through. Right? We don't want that air floating around in there and flying around. What we're doing is we're giving it some direction. So at this point, we're raising the pressure through here, and then we start to converge it back again, back into the blades. So it has some direction. It's set up and it's ready for the angle of attack on those fan blades. Sound okay so far? Not plausible. Okay. So this one here, you'll see this occasionally. You see that bungee cord there? That bungee cord is tying that because it's got probably a dead engine. I don't know where I got that picture, but it's probably a dead engine. what they do is they tie the fan so it doesn't turn while they're flying. Now, some of these engines have, because of the engine's greed for air, it's so greedy for air, it needs a lot of air to continue to run at high rotor RPMs. But maybe the airplane isn't moving at high speed, pushing that air into the front of the engine. So they have what they call blow-in doors. I'm going to show you a picture here. Okay, this is blow-in doors. You don't see these too much anymore on civilian airplanes, but you still see them a little bit on some military aircraft. Now what happens is, in this case, is the engine is so greedy for air, it's sucking air in at a very high rate. It creates a very low pressure zone in the inlet, and so they augment the flow of air or allow extra air to flow into the inlet through these blow-in doors. So these blow-in doors are actually sucked in because of the depression, the atmospheric depression. And once the aircraft picks up some speed, it then pressurizes that inlet area and blows those doors back shut again. I'm going to show you a picture here in just a second. Here's a Harrier. Y'all seen a Harrier before, right? This thing's going nowhere. It's just going up. Okay, so it's going up, but it's got no forward airspeed, so it's not really driving any air into the engine. But the engine still, like I say, is greedy for air. It wants air so bad it can't stand it. It needs that air to run. Well, these doors here will be drawn in or sucked in because of the depression up here in the front. Pulls the doors in, and as soon as this thing starts moving forward, those doors will blow back closed again. They're spring loaded, and they close right up, become an aerodynamic feature. Pretty simple. Here's another one. We look back here on the side of this thing. Same thing. Now this has got a long duct. The engine's mounted back here. It's got a long duct, but these extra doors that open here at slow speeds allow the engine to have enough air so that it can run at full speed. Blow-in doors. Used to be some civilian airplanes had those. Not so much anymore. So we have another duct design. It's called a divided duct. It's mostly on aircraft with center-mounted engines. I'll show you a picture of this here too. It's a divided duct. What it'll do is it'll pick up air on both sides of the fuselage and carry it down to a central duct, or if the engine is a twin engine aircraft, it'll carry some air down to one engine, some air down to the other engine. They'll both end up with the same amount of air. There's typically a plenum between the two that allows that air to commingle, so they both have the same amount of air. So this is a divided duct. This is one half of it. Now, a lot of times there's turbulence that rolls down the side of the airplane, so they'll put a strake on it. So it has a board right here which cuts the airflow off of the fuselage into the duct. So this, whatever's burbling here can't get into the duct and cause a problem. There's one of these on either side. Okay, and the cone, or the spike that I told you about, is part of the inlet. It's going to shoot the airflow around the engine core. It gives the air some direction of flow into the engine. Most of the time it's attached to the engine itself, the rotating part of the engine, but sometimes it is part of the aircraft itself. So so this is what we're talking about here. We'll take a little break in a minute here. So this is the column or the spike. In this case, this is a divided duct. As you can see, this part here is not attached to the aircraft because the air turbulent slides down the side of the airplane. You don't want that going into the inlet. So what they'll do is they'll have some break point here to where this is getting clean, smooth air, unobstructed and unspoiled. You can see the fan here on this engine. In this case, the fan runs right behind this fairing. This fairing here is part of the ductwork itself. Okay, why don't you take 15 minutes, we'll come back, we'll wrap this up now.